And now I'm very happy to welcome Sebastian Schwarz here on stage, who has a past in eSports. And if your parents ever told you that with playing computer games nothing is ever going to become of you, well, it brought him here. Meanwhile, after eSports, he did a detour over economics and data science and statistics and came back to Need for Speed Most Wanted and will be presenting his talk here on a competitive time trial for Need for Speed Most Wanted using deep reinforcement learning. Give him a very warm late night applause here on stage.
Perfect. Thanks for a nice introduction and welcome to my talk. So this is actually like my 10th CCC that I'm kind of attending, but mostly online, and my first CCC in person. And I'm very happy that I can kick it off with a talk today. And today I'm going to talk to you about a competitive time trial AI for Need for Speed Most Wanted using deep reinforcement learning. I mean, as already said, by day I'm heading a data and AI team at E.ON, but by night I'm focusing on my private projects, and this is really a project where my heart is in, and I'm going to tell you why in a second. So first of all, let's travel back in time with me like 15 years. And 15 years ago, I'm the person here on the right, if you can really see that. So 15 years ago, I was an eSport athlete. And at the height of my esports career, I was playing at Team Alternate, so that was the best Need for Speed team in Germany at the time, actually, together with my colleagues Gilbert and Niklas here. And I was playing Need for Speed Most Wanted, Need for Speed Carbon, Pro Street, and Shift. But my all-time favorite was Need for Speed Most Wanted. And probably hands up in this room, who has played this game, actually? Yeah, at least half of the room. Yeah, that's really nice. That's good to see. So it's almost 20 years old now, right? It's 19 years old this year, but it's still a classic. So introduction to the game. For those that don't know the game, it's an arcade racing game, and it's the best-selling game of the Need for Speed franchise with more than 16 million copies sold. And at the time, it was a popular esports title with major tournaments at Electronic Sports League, where I was mainly competing, and also World Cyber Games that I also competed in. And the game was played in races on circuits in 1-versus-1 mode. Usually, we're doing 5 to 6 laps with a standing start, and the first to complete all these laps wins the race, of course. And usually, all tuning, the game had featured tuning for the cars, all tuning was allowed. The WCG rules prohibited junkman parts, like special upgrades, and the best cars were the Lotus Elise for WCG rules, and the Porsche Carrera GT also for ESL rules, and depending on the track, one or the other was better. The track that I'm showing in the example, both cars are almost equal. You can do the same lap times with both, but I will train with the Lotus Elise. Side note, NOS, so Turbo Boost was kind of disabled because you could easily cheat with that, and collisions with other players were also disabled by ESL and WCG rules because the netcode was really bad at the time, and back in 2005 many people still had ESDN lines, so it was a bit of a laggy experience, right? So that was blocked. Good. And to set the bar high, I show you a really, really good lap on the track that I'm showing and I train my AI on. The track is called Heritage Heights, and at the time, 15 years ago, I uploaded this record on YouTube, and at the time, I know that it was the world record at the time. Nobody had a faster lap on this track by ESL rules. There are no official leaderboards, but I have never seen a faster lap at this time. I know that Gilbert on the other slide was 1/100th of a second slower, and one other guy was also matching the same time, but nobody was actually faster. And in order to show you what it's all about, I just show you this one lap that I uploaded on YouTube 15 years ago. So it starts on a straight. You basically go full throttle. You just keep it tight on the inside line. Then you enter the tunnel that's coming up on the left-hand side here. In the tunnel, you speed up. You hit the speed limit of 345 kilometers per hour. You go to the very right. This is one of 2 points where you need to brake, get the S-curves right and correctly without bumping into the wall. Then you speed through this next part here. Then you continue. This is like very easy. You just take the outside line here. Then this is difficult, inside line. Then you go to the outside line. You brake a little bit. You go through the underpass. Then you make a little jump and need to keep the car straight, otherwise you will lose speed. Here again, keep the car straight, otherwise you will lose speed. And then you follow through to the next corners. This is another part where you probably need to lift a little bit, or car can slip because of the border stones here. Then you turn left, don't hit anything of the garbage here, and then across the line, and then you do a 1.685, and you can remember that time already. Okay, that was 15 years ago. And then in 2022, Sony released a paper and made it to the cover of Nature magazine that was called, the second one here, Outracing Champion Gran Turismo Drivers with Deep Reinforcement Learning. And there was a predecessor to the paper that's called Superhuman Performance in Gran Turismo Sport using Deep Reinforcement Learning. And, you know, I read the papers and I saw like, and I thought to myself, I mean, how hard can it be, right? If Sony can make it, why can't I make it, right? So that's what I thought, and that's why I started this project. I started this project more or less 2 years ago, almost now, but I didn't consistently work on that. I just, continued now. And there were several problems because for me it was a start from scratch. So the game doesn't have any APIs that you can query, and no code is available from the Sony example or from the Sony paper. And not even the APIs they use for Gran Turismo are public, so you can't really use anything. So I needed to start from scratch. So the first thing I needed to do was to do the reinforcement learning is creating a custom gym environment. So the gym environment is kind of a Python class, if you will. That's a de facto standard for reinforcement learning. And essentially, it makes it easy to provide an action to the game. Action here is steering and throttle, basically. To get observation, you need to provide. That's like what the car observes. It's like telemetry and something where the car is located in the game. I will show it later on. A reward, so the faster you drive the car, the more reward you get. That's how the car learns how to drive, and the driver learns how to drive, the AI, basically. And a done indicator, which is kind of telling if an episode is completed. Episode is usually completed if a lap is complete or a time limit is reached. That's the first step. The second step, I needed to hack the game for an API because I needed to interact with the game in real time. I needed to read data from the game, and I needed to input something to the game. And for that, I used a virtual gamepad. And there's a vGamepad library in Python that kind of spawns a virtual Xbox 360 gamepad that I can use to steer the game. And the fourth step was then training the agent, and here I used a deep reinforcement learning algorithm using Soft-Actor-Critic. That's actually the same thing that Sony used in the first paper, using stable baselines free package in Python, which kind of provides stable baselines, because reinforcement learning is known to be notoriously hard to get it going, actually. And to just visualize it a little bit, this is how it looks like. So you see here on the left-hand side, we have our reinforcement learning agent. That's kind of a model. And what the model does is it observes something, a state in the game. Could be a picture, could be some data in my case, observes something and does an action, like steer left and throttle 30%, right? So it gives an action via the virtual gamepad that I have, the Xbox 360 gamepad, and it gives the action to the actual game, Need for Speed Most Wanted, which is abstracted by this gym class for reinforcement learning and by the NFS Most Wanted API that I created. And what the game then does, and the algorithm, it gives a reward. So depending on the action, the better the action was, the higher the reward. It gives an observation, which is like telemetry in my case, and something like where the car is located. And done indicator if the episode is completed. Yeah, lap is completed would be done is true. If the lap is not completed, done would be usually false. Okay, all right. Then I have one more slide, how it actually works. And this is the only slide with some formulas. I know it's late, but it's better to understand some formulas to see how it's going. So what I'm using as the agent is the so-called Soft-Actor-Critic algorithm for reinforcement learning. And the idea of this algorithm is that what you want to achieve is you want to maximize the sum of all expected rewards. So in the end, the agent will play with 30 hertz. So 30 times a second, it will input an action, right? And it will get a reward, right? And it will play until the lap is completed. So it gets a lot of rewards, and it wants to maximize these rewards. It wants to get the largest rewards possible. Yeah, that's called the exploitation. But at the same time, it also wants to maintain some exploration, and that's entropy. So you want to maximize the sum of the rewards and the entropy. Why you want both is the exploitation would make it faster if it has the correct line already, and the exploration makes it explore different paths. Yeah, at the moment you don't know, do you want to exit the tunnel on the right-hand side or on the left-hand side? Is it better to drive the corner on the left-hand side or on the right-hand side? This is basically why this is part of the target function. And what you want to do is you want to maximize this equation by finding the best policy, theta, pi, with parameters theta. Okay, what's the policy? The policy is kind of the driver, yeah? If you want to imagine it, that's the driver. So the policy is a function pi with parameters theta that basically predicts the next best action given an observed state. Yeah? That's the whole thing that this is saying. And this is parameterized by theta because the actor is a deep neural network with parameter theta. So this is the stuff I'm actually interested in, the driver. So once I have this function, I can just give it a state, which is an observation from the game, and it predicts the next best action. That's what I want, right? But in order to optimize it, I also need the critic, and that's the critic part in the SAC name. And the critic basically estimates the maximum achievable future rewards given the state and the action. And it discounts future rewards by a discount factor gamma. That means just that the next reward is more valuable than the future rewards that are coming up. Typical value for gamma is 0.99, so the next value is 0.99 times the reward, and the value after is 0.99 squared times the value, and so on, right? And this is what the critic is doing. So think about the critic as the driving instructor sitting next to the actor and telling, you could do better, you could go faster by doing this and that, and then the actor tries to basically accommodate that and fix the policy function for that. And in order to optimize that, what is being done essentially, it's overly simplified on the slide, but essentially the Kullback-Leibler divergence between the actor and the critic is minimized by training deep neural networks on a set of state. So that's the observation, action, and reward tuples that are stored in a replay buffer. So the replay buffer is kind of the memory of the agent. So all the situations that it has observed, it stores the observation, the action, and the reward in this buffer, and then it trains these models to proceed. And why is the Kullback-Leibler divergence? Because pi theta is actually not a single value, but it's a probability distribution function, and the Kullback-Leibler divergence is a distance measure on probability distribution functions. Okay, all right. Then implementing the custom gym environment. So this is how it looks like from the methods you need to implement. And basically 4 methods need to be implemented. And once you have that, it's pretty neat because then you don't need to worry about all these equations here and all the deep neural networks, because once this is done, you can just tell stable baselines to run it for you. That's pretty neat, actually. So this class inherits from the gym environment. In the initialization function, you just need to set the action space and the observation space. So basically the min and max values for the action and the observation. Then you define a step function. The step function takes an action from the agent and returns an observation, a reward, the done indicator, and some optional info array. That's the main function that's being called 30 times a second later on. Then you have the restart function that once an episode is completed, like a lap is completed, it resets the car to the start-finish line with a given angle and a given speed. And then you have a render function, which is pointless in this case because the game renders itself because it's playing in real time. But nevertheless, it's implemented and it kind of outputs a screenshot in a NumPy array. Okay, what's action in this case? Action in this case is the virtual Xbox 360 controller. So this gives a combined steering and acceleration input. The reward is the immediate reward for the action taken. So ideally, this would be the lap time. So ideally, you would just say, minimize the lap time. That's my target, right? That's all I want. But this is a very sparse reward. You would just see it after hundreds of steps playing in 30 hertz. So what you want is something that you can measure in every step. And what I take here is the delta and lap completion. So between each step, each time an action comes and then a reward comes, the reward is actually the delta and lap completion. So how much additional track have I surpassed in one additional step, right? So that's typically 0.005% or something, right? And the larger it is, the higher the reward. So it incentivizes the agent to go as fast as possible with each individual step. And if you keep the gamma relatively high, it optimizes the lap time in the end. Then you have the observation, and this is not an image, because taking an image takes a lot of time. Yeah. In the end, I want to train in 30 hertz and do these gradient steps and optimizing the neural networks in 30 hertz or above to play in real time. So I don't have a lot of time to capture a screenshot of the game and do some manipulations on that. And it also has some other drawbacks because the game has rain system and other stuff that would kind of make the image noisy. So what I do is I get telemetry from the game. That I will show in a second how I get that. I will calculate something like a LiDAR. So that's like the distance to the nearest borders on the left and right hand side in 1 degree steps, 100 degrees ahead, so 181 values. And I give it the tangents on the racing line, basically, and the angle with the coordinate system with that. That's what I call a GPS navigation system. And then I have the done indicator. The done indicator indicates if an episode has ended. Okay. And this is one of lap completion. It's the best case, a time limit reached, or if the car reverses. Because if the car reverses, very stupid stuff can happen. So if you don't limit that, what can happen, for example, is the agent starts at the beginning and then it turns around because, you know, when you cross the finish line in the incorrect direction, you have the maximum reward possible because you go from 0 to 100%. And, you know, I was observing that. I was like, well, what the fuck is he doing? So I stopped it from reversing, actually. Right? Okay, second part. Until now, I could implement the gym environment, but I don't have any data from the game. And even if I would use image data, I would need some information from the game, right? So some real-time data is required. So, for example, to calculate the reward, but also to calculate the features, or to either determine if a lap has been completed or not. So therefore, I use a mod for Need for Speed, partly, right? That's called Need for Speed Most Wanted Extra Options, and that allows me for some neat things that the game itself doesn't allow me for. So it allows me to have a windowed mode, to run the game in a window, that's required. Then more than 5 laps or 6 laps, the game is limited to 6 laps maximum. With this mod, I can do 127, which is nice. And I can teleport the car with a given location and a given speed and a given direction. That's what I use to reset the car after an episode has been completed. So usually the game crashes about after 12 laps for some bugs, right? But what I can do is I can teleport it back after episode is completed to the start. So I'm always in lap 1. Perfect. So I don't have this API, so I need to build it. Yeah, and the strategy with that is pretty simple, actually, but also complicated at the same time. So what I do is I access the game's memory, because all of the variables I'm interested in, they need to be somehow in the game's memory, right? Now the problem is the game's memory is like 300 megabytes, right? So, and I'm looking for single bytes in this memory, right? So what I do is I search the RAM for the right addresses for variables of interest, like the speed, for example. If I'm lucky, I find the value, and it's a pointer, so I can write down the address, and next time I start the game, it's the same address, and I can just read from it. Very simple. If something is instantiated, if it's an object, then it's dynamic, then I need to find a byte pattern, actually, a byte regex, to find that variable. And then, once I have these addresses, I just read the RAM using PyMem, so everything is written in Python. I just use PyMem, I give it the address, read from the address, and that's a nanosecond task to get the data. Very simple. And everything else, like this LiDAR feature, I calculate in real time in Python, which is a bit of a challenge because I have like 8 milliseconds to compute everything. Otherwise, it's not fast enough to play in real time. Okay, so this is an example how to track the XYZ coordinate of the game in the game's coordinate system and the speed. So essentially, you see, it's very easy once you have these addresses. And now the question is like, how do you get these addresses? Because that's the key of the talk actually for the game API. How does this work? So this is the table of the variables that I'm using and the corresponding addresses in the memory. And finding XYZ coordinate was pretty easy because with Need for Speed Extra Options, you can bring up a debug screen and it directly shows you these variables on screen. So I can just look up, you know, what's the value that's minus 365 in memory. And then I get probably 5,000 hits. Then I modify a little bit in the game, I pause the game, I check again. And I do that like 5 times and then I get these values and I just note down the address. Easy. The same thing is true for the angle. The angle is a 2-byte value. I couldn't make any sense of that, to be honest, what it really is. But it's a 2-byte value that's also known from the debug screen and from the reset function. And if you divide that value by 0x-fb12 and multiply it by 2 pi, you get kind of the Euler angle in the coordinate system. So that's kind of the direction of the car, right? If you think about how it's positioned towards northeast, southwest, right? Yeah, but only close to it, right? Then finding the speed again is easy because speed is displayed in the game, right? So you go to a certain speed, you pause the game, you look for that value. The only thing you need to make is assume that it's meters per second, not kph, right? And you find that value, you get like, I don't know, 500,000 hits. Then you try it again and modify the speed in the game. You check again in the memory, you narrow it down. So a value that was before like probably 33 meters per second and it's now 55 meters per second. And you narrow it down and after like 5 or so iterations, you just write it down. And then easy. So these ones were easy. Then there's a set of other variables that I'm using. So dx, dy, dz is like assigned direction vectors of the unit vector in the coordinate system. So that's also giving you the direction, like this angle, but much more precise. So with some trigonometric functions, I can easily calculate the Euler angle then. That's what I'm using in the end, because this is an approximation that I have no idea what this actually encodes, but it kind of works also. And how I found these is because there's a block of interesting variables around 00938 something that changes when you drive the car in the game, right? So I looked at these closely and I tried to make sense of it, and then I found these are the signed direction vectors of the car, and it makes sense. Then I have the spin of the car, which is like the signed angular velocity of the car in all directions, in radians per second. Acceleration was super hard to find. I spent like 3 nights just looking for acceleration of the game. So I wanted to have acceleration in meters per second squared. And of course, I had speed, so I could calculate it myself, right? And I did that. I could just calculate it from the difference in speed and the time that has passed. Easy, I get the acceleration, but it's like a bit noisy then. And how I got acceleration was actually, I looked at these addresses and I had 14 candidates that could have been acceleration. And then I calculated myself, I correlated with these values, and I found actually 2 values that are correlated with speed, but only slightly, right? And I looked deeply into that. And what I found is that the sign flips depending on the quadrant of the car in the coordinate system. That changed the correlation. And it's multiplied by a factor of 2048 for whatever reason. But if you divide it by 2048, you get acceleration in meters per second squared. And then I found some other variables for the surface the car is driving on. That could be like concrete or grass or wood, which is an integer. And that's, interestingly, it's for the left side of the car and the right side of the car. And that's a regex because that depends on the car and the instantiation of the car in the game. I found the lab and I can track steering and throttle inputs for my favorite controller, the Logitech RumblePad 2, which is not produced anymore, and the Xbox 360 controller. And that you find by just looking for the name of it and then offsetting it by 288 and 820. Okay, with that, pretty nice. I can map the track, right? Because I know the coordinates of the game. I can map a racing line that I did myself, right? That's the colorful line here. And I can map the track borders, and that's very simple because what I do is I just go around the borders because I need to map the track somehow, right? And I can't read it from the game. So what I did is I just spent like 10 minutes mapping the track actually, right? So sounds stupid, but it works. And then later on in the game, I use a lot of times the KD tree, so tree-based nearest neighbors, because I have the XYZ coordinate of the game in real time, and then I can calculate where it is on the track, right? By doing the nearest neighbors. I just check where's the nearest neighbor, for example, on the main trajectory, and then know that it's at 30% of the points I have, so 30% of the lap is completed. And I can also check if it's close to a border or there's a border collision if it's close to the border with some epsilon distance. Okay, perfect. Now I know telemetry, but I don't have any observation for where the car is actually located on the track. Therefore, basically the main idea is that I want to give it some vision. And therefore, I calculate a set of features. As I said, I calculate the slider, and I calculate some navigation, which is the tangent on the racing line and the angle that it forms with the coordinate system. So look at that picture, and you see that it's like a left turn is coming up, and the LiDAR I calculate looks like that, right? So you see the turn coming up, the distances to the next borders on the left side, on the right-hand side, and this is the navigation system. So the main trajectory is more or less straight from this point onwards. That's why it's hardly moving, but that's also an angle. That's also what the agent sees. That's the only thing the agent sees, actually. Okay, some demo time to just show you that telemetry can be read in real time. So this is me driving the car, actually, and here you can basically see what it's doing, and you can see how these values are updating. And if you look at acceleration, you know why it's difficult to find that, because it can change very quickly. You can just search it in the memory, right? And here's the LiDAR values. So this means 60 degrees to the left is 13 meters distance, and ahead. It's like in this case 167 meters, and to the right 46 meters. Okay, nice. So I implemented the API, and I have some vehicle functions like telemetry, LiDAR, if the vehicle collides with something, if the vehicle has airtime, so it loses contact to the ground, or if the vehicle reverses. I have some available methods for the lap time, lap completion that I need for the reward, and the angles ahead and the radii of the curves ahead, or the invice radii of the curves ahead. I have some other functions for the game to reset the vehicle to the start, or restart a race, or take a screenshot. Yeah, it's hardly used. And that's done. So now I can implement it. So to implement it, I need to give it a virtual gamepad. And therefore, I just give it a virtual Xbox 360 controller. And with that, it can steer with the left stick. It can, at the x-axis, it can steer left and right. Every value from -1 to +1 is possible. -1 is full left, and +1 is full right. And with the other stick and the y-axis, I can speed up and give throttle. And here, only a few values make sense. So essentially, for speeding up, only value -0.4, that's full brake but not reverse, makes sense. 0.7 is slightly lifting, and 1.0 makes sense, full throttle. For 99% of the track, it's full throttle, because it's called Need for Speed, of course, and not something else. So these are the values that make sense, right? The reward is the delta and lap completion. It's pretty simple. It's typically a value that's like 0.035%. The observation then is with telemetry, LiDAR, and GPS navigation system, as I said. It's a vector of length 494, because it has the telemetry here, the LiDAR, if it collides with something, if it's reversing, then the radii and the angle ahead, so it has some look ahead, right? And the last 5 steering inputs. And this is not trained on images, as I said, because even in the lowest resolution, which is 640 by 480, it's a lot of data to process, and you can't do that in 10 milliseconds, at least not in Python. You can do it in other programming languages, but not in Python, right? And so this is 500 times smaller than taking an image, right? And the done indicator just indicates when the episode is done, which is lap completion, time limit reached, 180 seconds here, or the vehicle reverses. All right. Training the algorithm then is pretty easy. So the whole machine learning part of that stuff is super easy. That's the full code of it, actually, right? So what you do is you instantiate a virtual gamepad. You create the environment that I have and give it the gamepad to steer it. Then you create a model for it. And the model is a Soft-Actor-Critic model. That's what it's saying here. It's a multi-layer perceptron, so that's a fully connected deep neural network. Gamma is 0.9, that's actually the default. I set a seed for reproducibility, and I set a buffer size for the replay buffer to 3 million. That's the maximum that fits in my graphics card while running Windows and the game in parallel. And then I just train it, and I train it for like 24 to 48 hours. And during that process, it learns to drive the car, right? And I can do that in 30 hertz on my kind of old gaming PC, which has a GeForce GTX 1070 and a fourth gen Intel Core processor. And I have some callbacks that saves the model because the game crashes randomly, which is annoying. And the game has a time bug, so the lap time gets totally incorrect after like 5 or 10 hours in the game. So by seconds, 2 seconds. So even the training, the time is really wrong. So I time externally. Nice. And now it's time for the final result. Yeah? So after training for 24 hours, this is how the result looks like. And let's see it now. And what you can see is, so the agent finds the racing line. It goes on the right-hand side to the tunnel, on the left-hand side to the tunnel, which is correct. It doesn't crash to any boundary. You can start it from any point in the game, and it finds its way back to the racing line. I can also move it to the left or crash it to the ball, and it finds always consistently the way to the start and finish line, really, really consistently. And it takes a little bit of a different line than I would do it. For example, here it goes to the left for whatever reason, but it's pretty nice. It also goes down to the tunnel here. It does the jump nicely. It finds here the line. It goes to the right here, weirdly. You can do that, but I think it's not the fastest. And then it continues like a human would do by completing the lap. And what you see is, in this instance, it's going to do 1 minute, 9 seconds, and 73 hundredths of a second, which is pretty fast, actually, right? Nice. And I only showed it briefly because of time, but what I can do now is I trained it only on this one car, and without retraining, I can just give it another car, right? And I told you the Porsche is equally fast on this track, and now I can just give it the Porsche, and it drives the same racing line, even though the Porsche needs to be steered very differently and braked very differently. It makes the lap. It only crashes slightly because it's not aware that the Porsche is wider than the other car, right? Because it doesn't have this data. But I'm just going to speed up a little bit. It also completes the lap, and it's not crashing, and it also does a really good lap time. It's just 1 second slower than the other car. And that's without retraining. So it has never driven this car, has never seen that car, and it works with any car in the game, actually. Looking at training progress here, you can see that this is episodes on the x-axis, so how many laps it was driven, and you see that it starts with a lap time of like 2 minutes or so, right, and then it drops down after like 500 episodes or so. It's at 113 lap times, and after, I don't know, in this case, 1,800 or so, it goes down to the best ever I saw from the AI, which are 1 minute, 8 seconds, and 90 hundredths of a second. And that's actually pretty fast. So the in-game AI is totally obliterated. That does a 133.17, so it's much faster. Casual gamer would do 118. A good player would do probably a 112, a pro a 19, and the record I showed was at 1686, and remember the AI is at 1 minute 8. So if you would do consistent 1 minute 8s, you would have won every lap, every race in the ESL, except for the top 5 maybe, right? So it's really fast. Okay, coming to the conclusion. So challenges and learnings. So I trained about 85 models. It was a good heating in the winter actually to run it on the graphics card in my room. I trained about 85 models, and even tiny changes in the model specification can really break everything, right? And what you need to really ensure is that you have a constant frame rate of the game and a constant frame rate of training, because otherwise it can't connect the action and the reward that I read from the game, right? Easy fix for that is turning on VSync in the game to 60 FPS. That's nice, and the other thing I can control myself, but it's not properly synchronized with the game, as you would see from other reinforcement learning applications, because in my case it's training really in real time. By the way, you can run this model without changing any files of the game. You can just run my Python script, and it does it for you. Some features are a bit noisy, like the LiDAR, because I calculate them myself using this KD tree algorithm. That's a bit hacky and creates a little bit of noise. That's why it's not superhuman yet. And yeah, to summarize it, it works well. If you would drive the car and you start my algorithm and just predict from this neural network that I trained, it's doing consistent lap times with variation of 0.3 seconds plus minus. It's accessible. You can do it on your computer. You probably might even have a better computer than I have, because mine is 10 years old. It's comparably fast, so it takes 24 hours to reach a really good lap time. The Sony claims in the first paper they only took 73 hours on 80 cars in parallel on 4 PS4s. And the other paper does a bit more also on driving techniques and strategies to overtake. They are using up to 1,000 parallel PS4s for the other paper. And it generalizes very well to other cars without retraining. However, it does generalize poorly to other tracks if there are situations where there's like a corner type it has never seen before, or a surface like grass that it has never seen before. Okay, perfect. I'm at the end of my talk. I want to thank my colleagues for keeping the motivation high, the guy from Need for Speed Extra Options for the mod, the guy from Sony AI that provided some insights, the guy from Trackmania Reinforcement Learning for a helpful comment, and of course my partner for being understanding when I was mentally busy working at the project. Very important. And I don't have the world record yet, so please check out my GitLab repository, make a pull request, and let's get the world record. All the code is open source and readily available. And with that, thanks a lot for paying attention.
Thank you, Sebastian. Now let's move to the Q&A. First of all, a check with the Signal Angel. Do we have any questions from the internet already?
Yes, we do.
We do. Shoot away.
Do you have any data on how much the critique had to correct the actions of the actor?
Oh, that's hard to tell because there's no statistic that's pointing that out. So what I do know is that the critic converges relatively fast when training the AI.
Okay, thanks.
Good. Thank you. Then let's start with microphone number 1 here.
Hello, hello. Do you have any plans on including traffic and some tuning setups within the model, specifically for the speedrunning community?
Yes. So traffic, first question, so the traffic is a bit difficult because I can't see it at the moment, right? Because I would need to see where the other cars are. I think it's possible to get this data, but currently I don't have this data. If it's possible, you can see it and then can also find some strategies to move around it. What you can do now already, even you can't see the cars. If it crashes into the car, it just doesn't care. It just proceeds, and then it's probably bounced to the left, but it just proceeds on its racing line. And the second question was on?
The second question was tuning setups, specifically for the speedrunning community.
Yes. So a nice thing that I also trained this for is when I was playing Need for Speed competitively, it was very difficult to find the best setup, right? I can give you the one for this car because I saved my save game for 15 years and I still know it, right? But it's notoriously difficult to find out which change in the setup makes it faster or not because you need to be very consistent. With this one, you could just change the setup and cycle through the setups and just train it and see which one is faster. Yeah, if it works in the end perfectly. Yeah.
Okay. Thank you.
Thank you. Let's move to microphone number 2 next.
Sure. First and foremost, great talk. Thank you. And my question would be that you mentioned applying action discretization for the acceleration. So you discretized, you said certain accelerations just don't make sense.
Yeah.
My question would be if you ever tried removing that, if there was an improvement, because to me it felt kind of a bit counterintuitive.
Yeah.
Maybe it's not always the best just staying discrete there.
You can just train it with leaving it out, right? That's definitely possible, and that's what I did at the beginning. Okay. But what I noticed then is it's very hard to distinguish for the agent if it wants to throttle 98% or 100%. And this just makes it slower, right? And it takes a long time until it figures out it always gives 100% when you speed up because you have a lot of grip in the game, right? That's why I included this step function, right?
Well, but you train a distribution, right? So if you train a distribution around your acceleration, then it could still figure out that it's, yeah, okay.
I mean, in the end, I give, that's correct. You can just leave it out and it should find itself, right? That's true. But there's no benefit in leaving it out. It's just faster. Also for initializing the agent, if it consistently speeds up and just goes forward, it kind of makes the lap. It's bouncing around a lot, but it kind of makes the lap. If you don't have this step function, it will also go backwards and forwards and backwards and forwards until it figures out that it needs to throttle up more than 50% at least to go forward, right? So it's a simplification, if you will.
Thanks.
Good. Short check with the Signal Angel. Something else from the internet?
We do have another question. Does the SOC model generalize to any track?
So it, as I said, it doesn't easily generalize to another track. So you can't just let it run on another track and it would work without any retraining. What you can do is you can use this model that you trained and then do fine-tuning on the other track because some basic driving techniques it already learned. Right? But it's not easily generalizing to another track without retraining.
Good. Microphone number 3 was next, I think.
So thanks for the talk. 2 questions. One is, the record was from you, and how much time did it took you to achieve the record compared to the 24 hours? And what will be the expected computing power to do it faster?
Yeah, okay, first question, I can only tell you that while I was playing this in my eSports time, I trained about 2,000 hours a year, right, on the game, right? That's what I can tell you, and that's what it kind of took to get there at the end of the season. And the second question is harder to answer. So I'm not really limited by computing power because as you see that by more and more episodes, the lap time doesn't really decrease anymore. So the way to get it faster is actually to get better features and to get that LiDAR without the noise that I currently have a little bit, or to get other features, right? That's what would really help. It's not limited on compute.
Thanks.
Good. And microphone 1.
So following up on that, what would be good features to improve the time? Do you have an idea?
A good question. So basically, I took the features that Sony was also taking in the other paper. So the only thing that I'm not taking is acceleration. So I take acceleration in the cast direction. What I'm not using currently is acceleration in the XYZ directions. That's what they are using additionally. And in the other paper, they are using not this LiDAR concept anymore, but like a set of features for the track ahead. This is something that you could try out, actually. This could make it faster, but you never know, right? It could also. I also had very good ideas, and then I trained it, and after 10 hours, it was just going to the boundaries all the time, and it was like, wow, really bad.
Good. We have time for one last question. Microphone number 4.
Thank you. Nice work. You partially answered my first question about whether some of the contenders take similar features, and you said yes.
Yeah.
I was wondering whether you are able to, as a human player or as an AI, to infer all these kinds of physics simulator features from what you see and what you hear, or maybe even there's more to what you see and what you hear than what you get from this.
So essentially, if I get it right for the second question, you're asking if I could just train it on the image that I would see and the sound from the game. Sony actually released another paper this year in summer where they did this, right? And this is possible, but it has a downside that it takes a long time to process this image if you would take it. But it's possible, yeah. Some people showed that it's possible for Gran Turismo, and also this Trackmania project. I think that was from this guy. Who created the V gamepad library, by the way, that's also trained on image data. So it's possible, it's just a bit slower.
How does it compare in terms of performance? I mean,
so nobody has really done it for Need for Speed, so I can't tell you. Yeah. The main downside why I didn't do it, first I thought this is the easy way because you don't need to hack the memory, right? You just get the image. I can take screenshots, by the way, in 300 FPS, faster than the game updates, right? But then even making it a grayscale picture and getting out a snippet of it in Python is 70 milliseconds at least, and that's too slow for me, right? You could try it with another programming language, and you technically should be able to do it, or don't do as many gradient update steps and just do it every, 5 seconds or so. You could try it, but it takes a long time, and also the game has changing weather, so also the image information would change and would not be constant, and the camera perspective would change it and all this stuff, so it's also not that easy.
Good. Thank you very much. Let's give him another applause.